A fighter jet screams down a runway in Chengdu, climbs past the speed of sound without ever lighting its afterburners, and the engine strapped inside its fuselage was designed, forged, and assembled entirely on Chinese soil. That is real. It exists. It's already flying on operational aircraft, and Western defense analysts have spent months quietly rechecking their own numbers because of it. Before this list is over, you're going to see a transport engine powering a fleet of strategic airlifters with 0 foreign parts inside it, a fighter engine that Chinese state media claims now produces more raw thrust than America's own F-22 power plant, and a completely different kind of engine that runs from a dead stop all the way to 6 times the speed of sound without ever switching systems. Every figure in this video comes from defense industry analysts, aviation trade publications, and verified government statements. Cross-checking military specifications that multiple governments would rather keep vague took real time. So if that effort is useful to you, hitting like and subscribe genuinely helps this channel keep doing that kind of digging. By the time we reach the top of this list, you'll understand why the phrase "China can't build jet engines" is quickly turning into one of the most outdated assumptions in modern aviation. Let's start with the engine that finally proved the doubters wrong in the first place. Number 6 on our list is the Shenyang WS-10C, and it earns the bottom spot here specifically because it's the engine that ended decades of genuine failure and finally gave China a domestic fighter engine that actually worked. Here's the backstory that makes this entry matter. China's earlier attempts at building its own jet engines, including programs known as the WS-6 and WS-8, were quietly cancelled after years of setbacks, forcing the country's Air Force to keep buying engines from Russia, a dependency that came with chronic reliability problems and left China's most advanced fighters at the mercy of a foreign supplier for their single most critical component. Here's the thing about that dependency. It wasn't a minor inconvenience. It was a genuine strategic vulnerability, the kind of gap that meant a foreign government could theoretically ground part of China's Air Force just by slowing deliveries. The mechanism behind the WS-10 program's eventual turnaround was brutally incremental. Early production runs suffered from turbine blades that couldn't handle the engine's own internal heat, and in its first 3 years of operational use, the program logged nearly 20,000 individual faults, a failure rate that would have ended most engine programs outright. Here's what actually changed things. Engineers systematically replaced the alloys in the turbines, compressors, and bearings, and the resulting WS-10C variant reached a thrust rating of around 142 to 147 kilonewtons, with a thrust-to-weight ratio approaching 9.5, comparable, for the first time, to the mature Western and Russian engines it was replacing, rather than a rough approximation of them. Think about what that actually represents. An engine reliable enough to finally give China's J-10, J-11, J-16, and J-20 fighters a genuinely domestic heart, ending a dependency that had shaped Chinese military planning for decades. Oh, but the WS-10C, for all its hard-won reliability, was still fundamentally a fighter engine built to power a single aircraft type. The next entry on this list had to solve a completely different problem, keeping an entire fleet of the country's largest aircraft in the air. Number 5 is the Shenyang WS-20, the engine now powering China's Y-20B strategic transport aircraft. And it earns this spot because of a detail buried inside a maintainer's own words that most people scrolling past this story completely missed. Here's the origin story. Developed by the Shenyang Aero Engine Research Institute and manufactured by Xi'an Aero Engine, the WS-20 is a large fan, high-bypass turbofan built using the core of the WS-10A as its foundation, adapted specifically to prioritize fuel efficiency and thrust over the raw maneuverability a fighter engine needs. Here's the mechanism that makes a high-bypass design like this fundamentally different from the fighter engine we just covered. Instead of channeling nearly all of its airflow through the hot combustion core the way a fighter engine does, a high-bypass turbofan pushes most of its air around the outside of that core, generating thrust more efficiently at cruising altitude. The exact design priority you'd want for an aircraft meant to haul heavy cargo across thousands of miles rather than dogfight at Mach 2. Here's the quote that puts this entry on the map. Yang Shushuai, an airborne mechanic serving with the 1st Air Force unit to receive this upgraded variant, stated on record in June of this year that the Y-20B has achieved full domestic production, that the WS-20 engine is fully independently designed and manufactured, and that its electronic components are entirely domestically. Here's the honest caveat worth including, because credibility matters more than hype. Western analysts examining the WS-20's architecture, a single-stage fan, 3-stage booster compressor, 7-stage high-pressure compressor, and 3-stage low-pressure turbine, have noted it's broadly comparable to Western engine designs from the 1980s. and it doesn't yet match the fuel efficiency, noise, characteristics, or advanced composite fan blade technology found in current generation GE or Rolls-Royce commercial engines. But an engine keeping an entire strategic airlift fleet independently supplied is a very different kind of achievement than one built to satisfy commercial airline economics. The next entry on this list is where China tried to solve that much harder commercial problem, and where the story gets a lot more complicated. Number 4 is the CJ1000, China's first domestically developed high-bypass turbofan built specifically for commercial aviation. And here's why it earns a step up on this list despite still being incomplete. It's the engine meant to finally free China's flagship passenger jet from depending on American and French suppliers entirely. Here's the backstory. China's C919 narrow-body airliner, built by the state-owned Commercial Aircraft Corporation of China, currently flies exclusively on engines produced by CFM International, a joint venture between America's GE Aerospace and France's Safran, meaning the aircraft. China markets, as proof of its aerospace independence, still depends entirely on a foreign engine to actually fly. Here's the mechanism behind why closing that gap has proven so difficult. Building a commercial turbofan isn't just about raw thrust. It demands an entirely different set of engineering priorities than a military engine. Extreme fuel efficiency across thousands of flight hours, noise levels that meet international airport regulations, and a maintenance interval measured in years rather than months. All standards that Western manufacturers spent decades refining through direct commercial airline feedback that Chinese engineers simply haven't had the same access to. Here's the number that shows how seriously this is being taken at the national level. China's newest 5-year economic plan, covering 2026 through 2030 and set for approval by the country's top legislature, explicitly calls for accelerating the certification and deployment of the CJ1000 after the engine's developer had originally expected to receive airworthiness certification back in 2025, a target that research reports indicate was delayed, specifically by mechanical setbacks and a lack of accumulated testing and assembly experience. Read that again. This is a national government explicitly writing engine certification delays into a 5-year economic plan, treating the gap as urgent enough to name specifically, rather than quietly hoping it closes on its own. Here's what makes this genuinely significant beyond the delay itself. A US-based economist tracking the situation noted that China felt the urgency to build its own aircraft engines, specifically because of past efforts by American policymakers to restrict engine exports to China, meaning the CJ1000 isn't just a commercial product. It's a hedge against the same kind of dependency risk that hurt China's military aviation for decades. But building an engine that merely closes a gap with existing Western commercial turbofans is still, fundamentally, playing catch-up. The next entry on this list isn't trying to catch up to anyone. It's trying to reinvent what the inside of a jet engine even looks like. Number 3 is a genuinely strange piece of material science, a shark skin-inspired structure. Chinese researchers say they've successfully embedded inside a turbofan engine, and it earns this position because, unlike everything covered so far, it isn't about matching an existing Western benchmark at all. It's an attempt to skip past it using a completely different engineering approach. Here's the backstory. Aviation companies, including Lufthansa, have already experimented with shark skin-inspired coatings applied to the outside of aircraft, thin ribbed films designed to reduce aerodynamic drag by mimicking the microscopic texture of actual shark skin, an application of what's called biomimicry that had previously been limited to a plane's external surfaces. Here's the mechanism that makes the Chinese research genuinely different. Instead of applying that same ribbed texture to the outside of an aircraft, researchers embedded a similar structure directly inside the internal components of a turbofan engine itself, aiming to reduce drag and improve efficiency at the point where air is actually being compressed and combusted, not just where it flows over the fuselage. Think about what that shift actually represents, taking a trick borrowed from nature and moving it from the easy external part of an aircraft into the extraordinarily hostile internal environment of a jet engine, where temperatures and pressures are far more punishing than anything the outer skin of a plane ever experiences. Here's the part of this research that points furthest into the future. The same report envisions hollow fan blades freed from some of the structural constraints of solid metal blades, incorporating internal skeletons and lattice structures similar to architectural engineering, specifically to substantially improve impact resistance, without adding the weight a solid blade would require. Here's the honest context worth including here. This remains research stage work rather than a flying, certified product, and turning a laboratory concept like this into a reliable engine component that survives thousands of hours of real flight is a genuinely different challenge than proving the idea works once in controlled conditions. But even the most exotic material science on its own is still just a component idea. The next entry on this list is where all of these threads, reliability, thrust, and advanced engineering, actually came together inside a single flying operational fighter engine. Before this list climbs any further, it's worth pulling back, because none of these individual engine programs happened by accident. They're all threads of a single, deliberate national strategy that China set in motion years ago. China officially launched the Aero Engine Corporation of China, a multi-billion-dollar state conglomerate with registered capital of 50 billion yuan, worth roughly $7.5 billion, and a workforce of nearly 100,000 employees, merging what had previously been a fragmented collection of research institutes and manufacturers into a single unified national champion. Here's the thing that makes that consolidation land differently once you actually sit with it. Chinese President Xi Jinping personally described founding the company as a strategic move specifically intended to make China an aviation power and modernize its military, while the country's then premier explicitly stated that breakthroughs in advanced aircraft engines would carry major value for both military strength and manufacturing capability. This is not a handful of separate engineering teams chasing separate goals. This is a coordinated top-down industrial strategy explicitly designed to end China's dependence on Rolls-Royce, GE, and Russian suppliers across every category of aviation at once: fighters, transports, and commercial airliners simultaneously. And once you see the scale of that ambition, the final two entries on this list, a fighter engine now being described as more powerful than America's own F-22 power plant, and a completely new propulsion concept aiming to erase the line between subsonic and hypersonic flight, stop looking like isolated technical achievements and start looking like exactly what they are: the leading edge of a national engine program that was explicitly built to eventually rival Rolls-Royce and GE on their own terms. Number two is the Shenyang WS-15, nicknamed Aimei, the engine now flying inside China's J-28 stealth fighter. And it earns this position because of a claim that would have sounded absurd coming from China's aviation industry just a decade ago: that this domestically built fighter engine now produces more raw thrust than the engine powering America's F-22 Raptor. Here's the backstory behind why this engine mattered so much. For more than a decade, the J-20 had been dogged by a persistent criticism from foreign analysts that it was a genuinely advanced stealth airframe held back by an engine that couldn't fully unlock its potential, first relying on imported Russian AL-31 engines, and later on interim domestic WS-10 variants that, while serviceable, never fully matched what a true fifth-generation fighter engine needed to deliver. Here's the mechanism behind what makes the WS-15 different. It's the first Chinese turbojet engine designed from its very first sketch specifically for a fifth-generation stealth fighter, rather than adapted from an earlier design built for something else, incorporating single-crystal superalloy turbine blades to survive higher internal temperatures, and a full annular combustor specifically engineered to sustain supercruise, supersonic flight, without ever needing to engage fuel-hungry afterburners. Here's the number that made this story genuinely global news. The WS-15 is rated at approximately 180 kilonewtons of maximum afterburner thrust, compared to the roughly 156 kilonewtons produced by the Pratt & Whitney F-119 engines powering the F-22 Raptor, meaning two WS-15 engines could give the J-20A more combined raw thrust than its most direct American rival currently flying anywhere in the world. Think about what that comparison actually means. The aircraft most Western analysts spent years describing as merely good enough may now be out-thrusting the gold standard of American stealth fighter engines, at least on paper. Here's the honest concession worth sitting with here because credibility matters more than a triumphant headline. A former PLA instructor quoted by the South China Morning Post directly acknowledged that a gap still exists between the WS-15 and the F-119 in areas like proven reliability and accumulated flight hours, and independent analysts have separately noted the WS-15 still lacks the thrust vectoring nozzles that give the F-119 superior close-in maneuverability, meaning more peak thrust on a spec sheet doesn't automatically mean the WS-15 has fully closed every gap with its American counterpart. But even an engine outmuscling the F-22's power plant is still, fundamentally, playing inside the established rules of conventional jet propulsion. The final entry on this list throws out those rules completely. Number one is a contra-rotary ramjet engine developed by researchers at the Chinese Academy of Sciences, and it takes the top spot on this list because it doesn't just improve on existing jet engine technology, it aims to eliminate an entire category of engineering problem that every hypersonic aircraft on Earth currently has to deal with. Here's the backstory behind why this matters so much: getting an aircraft from a standstill all the way to hypersonic speeds above Mach. 5 has always required two completely separate propulsion systems working in sequence, a conventional turbine engine to handle speeds up to around Mach 3, and then a separate ramjet system to take over at higher speeds, because a ramjet physically cannot generate thrust from a dead stop the way a turbine can. Here's the mechanism that makes this engine genuinely different from anything covered elsewhere on this list. Rather than switching between two entirely separate propulsion systems mid-flight, a transition point that has historically been one of the most dangerous and unstable phases of hypersonic flight, where shifting airflow and combustion conditions can destabilize an aircraft, especially while climbing or maneuvering, this new design uses two sets of compressor blades rotating in opposite directions within a single unified system, allowing it to function continuously across the entire flight envelope from a stationary start all the way past Mach 6 without ever needing to switch modes. Think about what removing that transition point actually means for hypersonic engineering, eliminating the single most failure-prone moment in the entire flight profile, the exact seam where previous hypersonic vehicle designs have historically been most vulnerable to instability. Here's the number that grounds this in real, tested engineering rather than a theoretical concept on paper. According to the project's lead researcher, a Chinese Academy of Sciences, academician, and engineering thermophysics expert, the prototype has already been completed and experimentally verified after more than 3 decades of sustained development. This isn't a rushed announcement timed for headlines. It's the payoff of research that's been quietly running since long before most of the engines earlier on this list even existed. Here's what the lead researcher said directly. In comments to China Science Daily, that developing new principle, engines like this one represents a strategic choice specifically aimed at breaking what has been, up to this point, a Western monopoly on advanced hypersonic propulsion technology and potentially surpassing it entirely. Here's the honest concession worth ending on. The completed and experimentally verified prototype is a genuinely major milestone, but it is still a meaningful engineering distance away from a fully weaponized or operational hypersonic platform flying real missions and translating any laboratory-verified propulsion breakthrough into a reliable, mass-producible engine has historically taken additional years, even for well-funded, mature aerospace programs. That is exactly why it's here at number 1. It isn't just the most powerful engine on this list, it's the one aimed directly at rewriting what an engine even is. So here's the full picture, start to finish. The WS-10C ended decades of failed domestic fighter engines and finally gave China's Air Force a reliable heart of its own. The WS-20 quietly proved, through the words of an actual maintainer rather than a press release, that China's strategic airlift fleet no longer depends on a single foreign component. The CJ-1000 is racing, with explicit national urgency, to free China's flagship commercial airliner from depending on GE and Safran altogether. Sharkskin-inspired internal engine structures are pushing biomimicry from the outside of an aircraft into the punishing internal environment of the engine itself. The WS-15 is now putting up thrust numbers that, on paper, outmuscle the engine inside America's own F-22 Raptor. And a contra-rotary ramjet, verified after more than 30 years of quiet development, is aiming to erase the most dangerous transition point in hypersonic flight entirely. What you're actually watching across this entire list is the same shift that happened to the global shipbuilding industry a generation ago. An entire technical category that Western nations assumed they'd permanently own, methodically rebuilt from the ground up by a country that treated every setback as a problem to be engineered around rather than accepted as permanent. China's jet engines were the punchline of Chinese aviation for decades. They aren't anymore. If breakdowns like this, the real engineering and the real verified numbers behind China's biggest aerospace pushes, are useful to you, hit like and subscribe, because there's more of this coming, including a closer look at what happens the first time a fully domestic Chinese commercial engine actually enters passenger service. So here's the honest question for the comments. Does a fighter engine outthrusting the F-22s on paper actually change the balance of power in the sky, or does the reliability gap analysts keep pointing to mean the real story is still unwritten? I read every single one,